Hi students, I want to discuss about thermodynamics. Thermodynamics is a branch of physics which deals with heat and other form of energies, that is called thermodynamics. Now, what is meant by thermal equilibrium? Thermal equilibrium means if two bodies are at same temperature, they are said to be thermal equilibrium. And what is meant by mechanical equilibrium? Mechanical equilibrium means if the net force acting on the system and net torque acting on the system, then it is said to be in mechanical equilibrium. Similarly, chemical equilibrium means net chemical composition remains constant throughout, that is called chemical equilibrium. Now, if systems are mechanical and chemical and thermal equilibrium, then it is said to be thermodynamical equilibrium. Thermodynamical equilibrium means it is in chemical equilibrium, mechanical equilibrium, and thermal equilibrium. That is called thermodynamical equilibrium. Now, to describe the thermodynamic process, we required some variables which are called pressure, volume, temperature, like that. Now, what is meant by, first of all, internal energy denoted by U? Internal energy means energy possessed by the system by virtue of its molecular motion and molecular configuration. That is called internal energy. Hence, internal energy is a sum of molecular motion, that is called internal kinetic energy, and internal potential energy, that is due to internal force of attraction, that is internal configuration. So, internal energy is sum of internal kinetic energy and internal potential energy. For ideal gas, there is no intramolecular force of attraction. So that for ideal gas, internal potential energy equal to 0 have only internal kinetic energy. Now here, the internal energy generally we express it in changes, that is change of internal energy du equal to final minus initial internal energy. Internal energy is a state function, means it depends only on initial and final state, independent of the path followed. Internal energy depends on temperature, means if temperature increases, internal energy increases, if temperature decreases, internal energy decreases. Now, work, work done by the gas during expansion. Similarly, when some external force applied, then it becomes compressed. So, work done by the gas during the expansion. For example, a gas enclosed in a cylinder with movable piston. Piston is free to move without any friction. Now the pressure of the gas inside is P. A is the area of cross section of the piston. Therefore, the force acting on the piston is F equal to pressure into area. Due to this force, it is moving out by a small distance. We say that dx. Therefore, the work done during this expansion dW equal to force into displacement, that is pressure into A into dx. P into A into dx is called change of volume. P dV, that is final volume minus initial volume. So this is the work done. Now here work done to increase the volume from V1 to V2, W equal to integral V1 to V2 P dV. Work is a path function, means it depends upon path followed, and We draw the graph between pressure and volume, that is called indicator diagram. Now the area under the indicator diagram will give the work. For example, if graph is like this, at pressure P, volume increases from V1 to V2. Then the work done during this process, W equal to P into V2 minus V1 in the area under this graph. Similarly, if it is like this, increases from volume V1 to V2 and pressure P1 to P2. Therefore, the work done during this process equal to W equal to, it is a combination of triangle and rectangle, that is half base into height, means V2 minus V1 into P2 minus P1 plus P1 into V2 minus V1. So this is the work done during this process. For cyclic process, the area under the cycle will give the work like this. We draw the graph between pressure and volume. Volumes changes from V1 to V2 and pressure changes from P1 to P2. Therefore, work done equal to, pi AB, that is pi into V2 minus V1 by 2. This is into P2 minus P1 by 2. Now it is clockwise, then work is positive. If it is anti-clockwise, work is negative. For example, like this, pressure and volume graph. Volume changes from V to V. At the same time, pressure increases from P to P. Then the work done W equal to 2V minus V into 2P minus P, that equal to PV. Now it is clockwise, so it is positive. If it is anti-clockwise, it is negative. And one more example, if the graph between pressure and volume is like this, volume changes from V2 to V, at the same time pressure increases from P2 to P. Now the work done during this expansion of the gas equal to, it is equal to area of the rectangle plus area of the triangle, that is P into 2V minus V, this area, plus area of this triangle equal to half base into height, that is 2V minus V, that is the base, into height 2P minus P, which is equal to PV plus half PV is equal to 3 by 2 PV. Next, zeroth law of thermodynamics. Zeroth law of thermodynamics. Zeroth law of thermodynamics is a fundamental law. It is basically based on temperature concept. For example, if two bodies or two systems are separately thermal equilibrium with third one, then the two bodies or systems are also in thermal equilibrium. Let us consider two bodies A and B having temperatures Ta and Tb are separately thermal equilibrium with third body C having temperature Tc. That is, A and C are in thermal equilibrium. Means TA equal to TC, and B and C are in thermal equilibrium. That is, TB equal to TC. Then automatically this A and B are also thermal equilibrium. So TA equal to TB. So this is called zeroth law of thermodynamics. Next, the first law of thermodynamics. First law of thermodynamics. First law of thermodynamics is based on law of conservation of energy. According to this law, if some quantity of heat, let we say that dq, is added to the system, it can be used to increase the internal energy and to do some external work. So, some quantity of heat is added to the body, it can be used to increase the internal energy of the gas, and remaining energy can be used to do some external work. Now, according to conservation of energy, dq equal to du plus dw. So, this is called first law of thermodynamics. dq equal to du plus dw. Now, if heat is added to system, dq is positive. Means if heat is absorbed by the system, dq positive. If heat is drawn from the system, we take dq as negative. If temperature increases, du positive. If temperature decreases, du negative. Work done by the gas, dw positive. Work done on the gas, dw is negative. Once again, if heat is absorbed by the system, then dq taken as positive. If heat released from the system or taken out from the system, dq is taken as negative. If temperature increases, du positive. If temperature decreases, du taken as negative. If work done by the gas because of volume increases, so dw positive. If work done on the gas, dw is negative because of decrease of volume. Now du equal to, from this, dq minus dw. Du means final minus initial internal energy equal to dq minus dw. Therefore, the final internal energy U final equal to dq minus dw plus ui. So this is the expression for final internal energy. Now, some drawbacks about this law. So this law cannot explain how much energy, means how much heat energy can be converted into internal energy and converted into work. But only some part of heat energy converted into internal energy and to do some external work. We don't know exactly how much amount of heat converted into work and converted into internal energy. And it cannot explain why heat always flows from high temperature to low temperature. These are the general drawbacks of this law. Now I want to discuss about specific heat of the gases. First of all, what is meant by specific heat? We know that specific heat is defined as amount of heat is required to increase the temperature of unit mass of the substance by 1 degree or 1 Kelvin. That is called specific heat. Hence we say that S is the specific heat equal to 1 by m into dq by dt. Now in case of gases, with rise of temperature, so at the same time, pressure and volume are changes. That's why it has two specific heat of gases. One is specific heat of the gas at constant volume Cv, and other one specific heat of the gas at constant pressure Cp. Now, to study the specific heat of the gas at constant volume, let us consider 1 mole. 1 mole of an ideal gas, if heat is applied to increase the temperature by 1 degree or 1 Kelvin. So at constant volume, that is called molar specific heat at constant volume, means amount of heat required to increase the temperature of 1 mole of an ideal gas by 1 degree or 1 Kelvin. That is Cv equal to 1 by N into dq by dt. So now units joule per mole Kelvin. Similarly, Cp, specific heat of the gas at constant pressure. Now, the amount of heat required to increase the temperature of 1 mole of an ideal gas by 1 degree or 1 Kelvin at constant pressure. That is called molar specific heat. Cp equal to 1 by N into dq by dt, units joule per mole per Kelvin. So now clearly Cp is always greater than Cv. Now the difference Cp minus Cv equal to R, and Cp by Cv, the ratio of the two specific heats is called gamma. That is called ratio of two specific heats. Clearly we know that Cp minus Cv equal to R. So where Cp is the molar specific heat of the gas at constant pressure and Cv is the molar specific heat of the gas at constant volume equal to universal gas constant. Therefore, Cp equal to Cv plus R. That's why Cp is always greater than Cv. And again Cp by Cv equal to gamma. Now from these two equations we get Cp minus Cv equal to R, then Cp equal to gamma into Cv, therefore gamma Cv minus Cv equal to R, therefore Cv equal to R by gamma minus 1, and Cp equal to gamma R by gamma minus 1. Now gamma is the ratio of two specific heats. It relates with degree of freedom. Gamma equal to 1 plus 2 by F, where F is the degree of freedom. Now degree of freedom is defined as the number of independent coordinates are required to describe entire motion of the molecules. For monoatomic gases, degree of freedom is 3. For diatomic gases, degree of freedom is 5. For tri or polyatomic gases, F equal to 6. For monoatomic gases, degree of freedom F equal to 3. Therefore, gamma equal to 1 plus 2 by F. So, gamma equal to 1 plus 2 by F, that is 1 plus 2 by 3 equal to 5 by 3, like helium, argon. For diatomic gases, F equal to 5. Therefore, gamma equal to 1 plus 2 by 5 equal to 7 by 5. For tri or polyatomic gases, gamma equal to 1 plus 2 by 6, that equal to 4 by 3. Therefore, Cp minus Cv equal to R, and Cv equal to R by gamma minus 1, Cp equal to gamma R by gamma minus 1. Then for monoatomic gases, Cv equal to R by 5 by 3 minus 1 equal to 3R by 2, and Cp equal to Cv plus R, that is 3R by 2 plus R equal to 5R by 2. Similarly, for diatomic, Cv equal to R by 7 by 5 minus 1, that is equal to 5R by 2, and Cp equal to Cv plus R, that is 5R by 2 plus R equal to 7R by 2. For polyatomic gases, gamma equal to 4 by 3. Therefore, Cv equal to R by gamma minus 1, that is R by 4 by 3 minus 1, that is 3R, and Cp equal to gamma into Cv, that is 4 by 3 into 3R equal to 4R.